So I have some progress to show you on my current eyeball numbers I'm drawing. It is basically done. I think I might add in a little more shading, but this is about it. So I'm going to explain a little bit of the numbers as well. So this is the eyeball. This is one of the many pieces I'll be drawing on the eyeball actually. So it's not going to be just one piece. This is a nice 3/4 angle, so you can see, and with a nice slice, so you can see the interior view of the eyeball as well as the exterior. And it goes out from the optic disc and the optic nerve to the optic chiasm, up to the lateral geniculate nucleus, and then back out, swooping to the visual cortex, so going into the occipital lobe here, where the numbers get really big, or fairly big for me anyway. So a quick rundown of the numbers. We can start at the front of the eyeball. So the iris, I've chosen to draw, this is an iris with heterochromia, so you have multiple colored iris here. It's drawn with a chemical formula for melanin. Don't know how well you can see the detail here. You've got some nice blue, green, and brown. It's actually a lot of numbers in here, so this might take a little bit. But the inside of the pupil, the outside of the pupil, this is drawn with its range of size. Basically, it's 2 millimeters to 8 millimeters. The cornea is drawn with its index of refraction. The lens is also the index of refraction. It also has Snell's law in it. I spent a lot of time learning how to do the math on refraction, so I don't know if everyone will like this, but this speaks to me, and I didn't want to forget it. I talked about this earlier, so the ciliary processes are drawn with the rate at which they create aqueous humor. They produce aqueous humor. Come on, focus. Oh, it was focused for a second. There we go. Which is 2.5, 2.3. It's 2.5 microliters per minute, per hour. Nope, this is per minute. Okay. The cool, interesting part about this mathematically is it correlates with the canal of Schlemm, which is drawn with very simple numbers 90 and 100. And that represents the fact that the aqueous humor, which is filling the anterior portion of the eye here, is completely replaced every 90 to 100 minutes. This relationship is important. If it starts slowing down, for instance, and replacing every 120 minutes, you're going to have a buildup, being that this is still producing aqueous humor at 2.5 microliters per minute. And if you get a buildup, you're going to increase the interocular pressure, which can have some negative side effects like vision loss. And it's yeah. So I really like this correlative data. I think this tells a nice little story. Back here, I have, for the choroid, I chose to use math that has to do with interocular pressure, accounting for venous pressure as well as the aqueous humor. That's really small. I think it'd be a lot easier for you guys to see this in person. You can see that. And like the choroid tunic it nurtures the eye with blood, so it's blood supply, but an oxygen supply, and it's the red you see there. Let's see. The black line, that's meant to represent the pigmented epithelial layer, which is behind the retina, and this absorbs light. It also produces retinol to replenish the photoreceptors once they've been bleached, which is what you call it when a photoreceptor has basically absorbed the photon of light to the point where it's ready to send the signal down, so it's been bleached. So choroid, pigmented layer. The retinal layer, so the neural tunic here, which I have sort of an orange. I drew that. I have a few things. I have the chemical formula for glutamate, which is really important in signal transduction. It's a neural transmitter. Right there you can see I have opsins for specific opsins. These are opsin proteins that are important in phototransduction for the photoreceptors, and you have one specific for the short wavelength, medium wavelength, and long wavelength cones. There's also one for the rods, which is different. And I have some wavelength sensitivity. Moving on from there, I'm going to jump right to the fovea. So the fovea here, the center is mostly, so this is peak wavelength sensitivity for the 3 cones. The center of it is primarily long wavelength sensitivity, which is red. There's also a fair amount of green, which is a medium wavelength in the inside. And then on the outside of the fovea is where I have a fair amount of short wavelength for blue. And then as you move out, you've got, they get larger and further apart, just to slightly represent the dispersion of density and size of the cones from the fovea to the periphery, which, I mean, by the time you're here, they're far reduced. And you have very few cones this far out. And we're looking at a dome shape, an inverted dome shape of the retina across there is what we're seeing. As we move away from that, I have a chemical formula for retinol, which is important in phototransduction and is involved in rods as well. And this is all information about rod cells, which is in our periphery. I also have some little bits of, every now and then you'll see a word scotopic, which is the term for basically the fact that rods are good for seeing light seeing in the dark, whereas these are photopic, so they require high levels of light, the cones. The optic disc here is where, so all the retinal ganglion cells travel down to the optic disc to leave the back of the eye to the optic nerve. This is, of course, the blind spot because you have no cones here. So this is, we've accommodated to this blind spot so we don't notice it at all neurologically, that we're not seeing something. That is drawn with the degrees away from central vision, which is 15 degrees off from the fovea, and also the degree range of blindness, basically, which I think is 5 to 7, and that's there. And let's see, what else we want to show you. Yeah, I told you about this guy. I have collagen around the sclera, and I have lots of hidden words for sclera and collagen and fibrous tunic. And then as we go out the back, and so just imagine this goes behind there, it's connecting to the optic disc there. This is the optic nerve. And trailing out, I have a combination of, we have membrane potential. So if you see VM, that's from membrane potential. If you see the big E and little k, that's the Nernst potential, or the I can't think of the word right now. Anyway, it's equilibrium. It's the Nernst equation, and that is, I'll explain that later. It's in another video. And that's the chemical formula for glutamate again, which is an important neurotransmitter in the central nervous system. And it moves out, goes to the optic chiasm, goes up to the lateral geniculate nucleus, the LGN. This is where the first visual transforms happen. No visual transforms happen in the retina itself. And then out, and wisps out back here to the occipital lobe, into the visual system of the brain. I think that just about covers it for the numbers that I chose to use here in my first large numbers I'm drawing of the eyeball. I hope you guys like it. The notes on this were extreme. Honestly, I studied all over the place for this, and there's a lot of things that I've learned that I didn't include in this drawing. Other things I think are quite wonderful, but that I didn't have any math that I felt represented it. So this is sort of one of the things that I juggle with when creating artwork, is concept correlating and versus the data, the math. So yeah, this is where I am right now. Next, after I finish this, I think I'm going to work on the tapetum lucidum, which would be, so where we have the pigmented epithelial layer. Nocturnal animals like cats and dogs and cows and sheep, they have the tapetum lucidum. There's also the tapetum choroid, I think is what they call it. And this, for them, it would reflect light back out. And so that when the light comes in, it bounces it around, so they get increased light absorption for night vision. And that's why it gives it their eye shine. For that piece, I don't think I'm going to use this kind of a background. I'm thinking of doing that piece on scratchboard, so I can capture the striking difference of the colors versus the darkness. Anyway, so I hope you don't mind if I branch off from this color scheme. I would like your opinion on that if you've managed to listen to this video, watch this video for the entirety, if you wouldn't mind a piece that's on a black background, so like my other scratchboard pieces. So that is where I am, and I'm going to write more about this, but as far as the gallery show that we were talking about for late in the year, I would like to have your guys' opinion on that. I can have an open studio show in December to show you where I'm at now. Because of the fact, I can turn this around, you can look at my face if you'd like, I suppose. Because of the fact that my research went long, I haven't created as much work as I had intended to have for a gallery show. I'll probably have, I have quite a few of the numberism specimens. I have this piece, and I may have another large piece that I'm working on. So really, the gallery show is to bring you guys into my lab and to show you my process and the work that I've made so far. So please let me know. Do you want to come in now? Do you want to come in December and see the work, or do you want to wait? We could also do this in January to have the show. I think that's all I'm going to say in this video. This is a long video. I'm happy with this piece, and I've gotten back into the art flow at this point, so I'm stepping a bit farther away from the research and in this part of my process, and I'm enjoying what's happening, and I'm hoping that you guys are enjoying what's coming out of it. So I guess until next time, thank you, bye.